Right, greetings. So today we are going to be looking at nature of roots of quadratic equations. So basically this is a grade 11 CAPS syllabus. So we are going to delve deep and explain what does it mean nature of roots and which are the conditions or the natures of the roots that you find in quadratic equations or for the parabola. Right, so let's say you are given y is equals to ax squared plus bx is equals to plus c, right? And then they tell you that find the value of x, right, when y is equals to 0. So to do that, we use completing the square, and then we find the quadratic formula. So we can determine the x-intercepts of this parabola or quadratic equation. So the x-intercepts are also termed the roots of the quadratic equation. We use the quadratic formula. So the quadratic formula is a result of completing the square. So by this lesson, you should have done completing the square. So this formula is a result of completing the square. So x will be equals to negative b plus or minus square root of b squared minus 4ac all over 2a. So this is the result of completing the square, which by now watching this lesson you should be able to do completing the square of a quadratic equation. Right, so in this quadratic formula, from the quadratic formula, we have got what we call the determinant. Some call it delta, some call it determinant, some call it the discriminant. So this delta, which is b squared minus 4 multiplied by a multiplied by c, is called the delta or the discriminant, or some call it the determinant. So we use this delta to determine the nature of the roots of the quadratic. It will tell us what kind of roots, if any, they are going to be. And we can even have an idea of what the graph will look like. Okay. So delta is the one that we use to determine the nature of the roots of a quadratic equation. So in this case, the most important things are it's either you use delta, discriminant, determinant, and you must know that this delta or discriminant or determinant is used to determine the nature of the roots. So now let's look at the nature of the roots. So when d is equals to b squared minus 4ac, we can take this and calculate for any equation such that if our delta is less than 0, what this means is that the roots are non-real, which means there are no x-intercept, and the graph usually is suspended above or below the x-axis, so which means there is no x-intercept. Okay, and then if our delta b squared minus 4ac is greater than or equal to 0, then we can say that the quadratic equation has got real roots. This is general. So basically the graph will have either one x-intercept or two x-intercepts. So which means this is general. We are going to break this down, right? We're going to explain it further. So what we just know is the general rule that the roots are real, but we can be specific when we break this determinant down. So if we are given the identity b squared minus 4ac is greater than 0, we can explain it further. We can start by b squared minus 4ac is equals to 0. So in this case, the roots are real, they are equal, and they are rational, right? So graphically, the x-axis will be tangent to the parabola at the turning point, right? That means the graph will just touch the x-axis, which means there is only one x-intercept. So when you solve this quadratic, you see that it has got two equal values, and those values are real, equal, and rational. And then if your determinant is greater than 0, but that determinant is a perfect square. So what this means is that the roots are real, unequal, and they are rational, right? And graphically, the parabola will be having two different roots. So very important there. And then if your determinant is also greater than 0, but the determinant is not a perfect square, so the roots will be real, unequal, and irrational, right? So graphically, again, there will be two roots or two x-intercepts. So you can see the difference. Now we've broken down the determinant. Generally, the moment you will see that your determinant is greater than or equals to 0, then you can know that the roots are real. But you can be specific. If the determinant is equals to 0, then it will mean that the roots are real, right? So which is important here, right? The roots are real. Can you see? If your determinant is equals to 0, the roots are real, the roots are equal, the roots are rational. And graphically, it means that the x-axis is tangent to the parabola, right? And you usually have one x-intercept, right? And then if your determinant is greater than 0, you can see that, and then they say, but it's a perfect square. So if it is a perfect square, then what that means is that the roots are real, unequal, and rational, and you will have two roots or the x-intercept. And then if your determinant is greater than 0, but it's not a perfect square, then the roots are real, unequal, and irrational, right? And the parabola will have two roots or intercepts, right? Let's just explain this graphically also, right? So graphically, let's say we want to explain if b squared minus 4ac is less than 0, given the function f of x is equals to ax squared plus bx plus c. So we can represent this graphically. So we were guided by the value of a. If a is less than 0, which means there is a maximum, or there is a maximum local point, right, or a maximum turning point, you see the graphs will be suspended below the x-axis. If a is greater than 0, which means there is a minimum local point or turning point, then the graphs will be suspended above the x-axis. You can see in both cases, when our determinant is less than 0, our parabolas do not touch or cross the x-intercept. So this is our x-intercept and this is our y-intercept. You can see that in these both scenarios, the graphs do not touch or cross the x-axis. So there are no x-intercepts. Moving on, right? If our determinant is equal to 0, so when it is equals to 0, which means that, remember we said, given the function f of x, first let's look at the two scenarios. Either a is less than 0, of which there is a maximum local point, so the x-axis will be tangent to the turning point of the graph. And if a is greater than 0, which means we've got a minimum local point, you can see we have got the x-axis being tangent to the turning point. So you can see the two scenarios. This is our x-axis and this is our y-axis. In both situations, the x-axis is tangent, which means the graph does not cut, but it touches the x-axis, because the x-axis becoming the tangent at the turning point. Okay, moving on, let's look at another scenario of the determinant when the determinant is greater or equal to 0. So in this case, we are not bothered about if it's perfect square or it's not a perfect square, the determinant, but in both cases we will result in a same situation. So if a is less than 0, which means there's a maximum point, the graph cuts the x-axis at 2 points. Can you see that? The graphs cut the x-axis at 2 points, right? So that is the same when x is greater than 0, where there is a local minimum point. So you can see we can use the nature of roots to help us describe how the graph would look like. Okay.